We were talking about the eigenfunctions for angular momentum. And you need to be ready because this is going to be kind of a long development, but of course it's well worth it. So the first thing we're going to do, we're going to be in spherical coordinates. So I'm going to express Lx, Ly, and Lz in spherical coordinates, remembering, of course, that momentum is h bar over I times del in three dimensions. So first thing we do is we write the del operator in three dimensions, which is this expression right here, r d dr theta times 1 over r d d theta plus phi hat 1 over r sine theta d d phi. That should be fairly familiar to you by now. And we're going to write the L operator in terms of r's and p's, or r's and del h bar over I del, in the following way. And you notice some terms will drop out. For example, I have an r cross r hat term here. Of course, any vector cross with itself is going to give us 0. So that first term drops out. Second term, where I have an r cross theta, where that's going to give me a phi hat and dd theta. And then the third term, r cross phi hat, will give me a minus theta hat. And we can, then what we want to do is to convert this expression, and this is really ugly, to Cartesian coordinates. In other words, we want to write our unit vectors, theta hat and phi hat. Remember, we don't have to worry about r hat. Theta hat and phi hat in terms of I, j, and k components, as though we're in Cartesian coordinates. And this is what results: cosine theta, cosine phi. In the I direction, cosine theta, sine phi. In the j direction, minus sine theta. In the k direction, for theta hat, for phi hat, we get minus sine phi in the I direction, minus cosine phi in the j direction. When I insert those into my angular momentum operator, this is the mess that I have brought. As we can see, this is a rather long expression, but it should cover the bases in terms of what the operator would look like in Cartesian coordinates. And of course, if I look at it more carefully, I might like to break it up into x, y, and z components. So I get Lx, Ly, Lz, hence the need for Cartesian coordinates. When I do that, I take all my I terms, and that becomes Lx. I take all my j terms, that becomes Ly. And of course, my k terms become Lz. And when I do that, this is what I end up with. And so I have my Lx component, Ly, Lz. In addition, as a kind of a bonus, I'm going to put up here my L plus minus component, which you remember is Lx plus or minus I Ly, and we have this expression that will cover that. And just to keep in mind, one of the shortcuts we can take is to use cosine phi plus I sine phi. Of course, I can write as e to the plus or minus I phi. That might make things a little bit cleaner. So my L plus minus operator looks like plus minus h bar e to the plus minus I phi times this term, dd theta plus or minus I cotan theta d phi. And so that's cotan theta d phi. Okay. Now, let's do the following. Let's apply Lz. Start with that. We'll apply Lz to my eigenfunction. So you have to bear with a lot of algebra here, but as I say, it's going to be well worth it. So I'm going to apply Lz to FLM, and that's going to be equal to plus or minus h bar e to the plus minus I phi d theta plus or minus I cotan theta d d phi applied to f Lm. And that's going to give me, I'm going to write this as Lz applied to FLM also gives me h bar over I df Lm d phi, and that I'm saying is equal to m h bar f Lm. That means if I look at these two expressions, FLM must be some function of theta, we'll just call it g of theta for now, times e to the I m phi. So g of theta will be a constant of integration with respect to phi, but it can still depend upon theta. F sub Lm is simultaneously an eigenfunction of L squared with eigenvalue h bar L plus 1. So that means L squared applied to F Lm would be equal to this applied to F Lm as well. And so I can write the following. I can write this, again, bear with the large number of terms. I can write this as L squared F Lm is equal to L plus L minus, as I did before, plus Lz squared minus h bar Lz F Lm. And I can write that as h bar e to the I phi d d theta plus I cotan theta d phi times a minus h bar e to the minus I phi times df d theta minus I cotan theta df d phi minus h bar squared, second derivative of f with respect to phi, minus h bar squared over I df d phi. All equal to h bar times L plus 1 times f Lm. I'm going to make the following substitutions. I'm going to substitute dFLm d theta is e to the I m phi dg of theta d theta, and df Lm of d phi is equal to I m e to the I m phi times g of theta. So if you remember that, we put all of that together and create yet another mess. I get minus e to the I phi d theta plus I cotan theta d phi times e to the I m minus 1 times phi dg of theta d theta plus m g of theta cotan theta plus m squared g of theta e to the I m phi minus mg of theta e to the I m phi. Further algebra, if I cancel the e to the im phis all around, I'm going to get minus d squared g of theta, d theta squared minus m dg of theta, d theta, cotan theta plus mg of theta, cosecant squared theta plus m minus 1 cotan theta dg of theta d theta plus m minus 1 times 1 plus cotan squared all times g of theta. Simplify it, it becomes minus d squared g of theta, d theta squared minus cotan theta dg of theta, d theta plus m squared g of theta, cosecant squared theta is equal to L times L plus 1 times g of theta. Make it simple, let's multiply through by sine squared to get rid of these cosines and cosecants, rather cotans and cosecants, and I get something that looks a little bit better. Sine theta, second derivative of g with respect to theta, plus sine theta cosine theta, dg of theta, d theta, minus m squared times g of theta is equal to minus L plus 1 sine squared theta g of theta. Now we can just write this out one more time so that it really does look familiar to us after all this work. We get sine theta d theta of sine theta dg of theta d theta plus L times L plus 1 sine squared theta minus m squared all times g of theta is equal to 0. If we compare this equation with the differential equation we used to solve for capital theta of theta in our three-dimensional analysis a couple of lectures ago, you're going to see that they're completely equivalent. So what that tells us is the solution, the theta part then, theta of theta, then is just the solution will just be the spherical harmonics y sub Lm as we had them before. So that is to say my spherical harmonics are also exactly the normalized eigenfunctions of L squared and Lz. Isn't that fortuitous? So by solving the Schrödinger equation in 3 dimensions using the separation of variables technique, we constructed simultaneous eigenfunctions of 3 commuting operators. That is to say h, L squared, and Lz. So we can write then h psi is equal to e psi, L squared psi is equal to h bar L, L plus 1 psi, and then Lz psi is equal to m h bar psi. Interesting. Now, there's something to that sort of sticks out here that we have to be a little bit careful about. When we did this, through this colossally long operation, we found that L and M were integers. Okay, fair enough. However, when we did the algebraic approach, where we used the raising and lowering operators, that approach also allowed for half-integral values of L and M. This method only allows for integral values. That might be a bit of a worry. However, we'll have spin come to the rescue. In the next section, which will be on spin, which of course we talked about much earlier in the course, spin will come to the rescue and allow us to sort of find a way to bring in half-integral values of L and M as well. Let's pick up with that next time.